Okay, so the theme for today is to recall, first of all, what did we call last time? The round complex together with Maxwell's version using Hodge operator. And then we will prove after that, the so-called Huckleberry lemma. And this will finish our discussion of differentiable phenomena on a manifold, basic differentiable phenomena. The Poincaré lemma says that if M is diffeomorphic to a, doesn't matter, diffeomorphic to a cube, for example, then all of the cohomology vanishes. So every closed form is exact. And then after that, we will go to a bit of integration theory. So this is more or less, everything here is differentiation, B operator, and so on. I hope I have time for this integration today. I may not. A bit of integration. In particular, I will explain how to prove Stokes' theorems. Stokes' theorem. A sketch of Stokes' theorem. There are two basic theorems in mathematics at the beginning. One is the rank theorem, and the other is Stokes' theorem. That's God agreeing.
Why we didn't learn these two most basic theorems in mathematics?
What?
Why we didn't learn it in the first year?
That's because I will not comment on the first year. Look, the first year in mathematics, historically, and I'm not sure I agree with it, in fact I don't agree with it, is like learning Latin in high school. It means you understand how to formally do certain things. For example, you understand how to write mathematics. You understand the simple logic of given epsilon and delta, this type of thing, right? It's something like Latin in high school, but it has almost nothing to do with mathematics. Okay. So let me recall this just for fun. Let's put Durham on top. So the manifold is connected. So the constant functions. Then you have the D operator. You get one forms and two forms, and so on. And I'm only going to do this in dimension 3, which is the usual dimension that you are involved with when you first meet this subject. And I'm only going to do it for M equal R3. And in order to discuss the matter, as we learned last time, we need an orientation form, which I will fix as the standard orientation form. dx1, dx2, dx3. So that's the standard orientation on R3. A nowhere vanishing top form. And now, below all of this last time, we had some fun. Maybe I don't know. Let's start having fun in the middle here, maybe here. This is isomorphic to the vector fields on M. And I emphasize that we use not only the standard orientation, but here we use the standard coordinates. So if you have a vector field is written, so let me just write this one time. I don't know which way I want to do it, it doesn't matter. So if we have a form, say A dx 1 plus B dx 2, I mean, I'm boring you with this, but we're warming up now. This gets mapped to the vector field A, D, so it's just the duality. Just duality. D dx 1 plus B dx 2 plus C dx 3. So this is the duality which allows us to interpret d of a function as a gradient. I talked about that at great length last time. And now parallel to this down here, we have the gradient, which if you take d, you get a gradient of a vector field, you get another vector field. And that comes from taking d of...
No, you don't have gradient there.
Hmm?
You don't have gradient there.
We don't have gradient? Oh, no, I'm sorry. We have to start here, right? Okay. Yeah, I started too far forward, right? So d of a function is interpreted using the standard coordinates as gradient of the function. Right? Okay, and last time I talked about what is curl. That is here. And that goes from here to here, and last time I talked about divergence, which goes from here to here. So these are just functions. Okay. Well, I think I talked intensely about why gradient is well defined. It's simply d, but interpreted by duality here. This curl, in the literature, we talked about after class, sometimes people call this rotation, or rotation. I don't know, we had some big debate about what you call it. What do you call it? True?
Curl.
Curl, okay. So, okay. Now what is that? Well, you want to go from here, from one form to two forms, but interpreting this as vector field. So how do you do it? You start with a vector field, interpret it as a one form, take d of it, right? And somehow you have to get back to a one form which you interpret as a vector field. Right? So there are operations here. So we've talked about Durand. The lower level here I'm dedicating to Maxwell. And the other operations are Hodge. There's the Hodge operation here and the Hodge operation here. Okay. So again, if you want to take curl of a vector field, you interpret it as a one form, take d of it, go back by the Hodge operator, and interpret that as a vector field and land here. Right. That is curl. And I talked about last time what that is. Let me just say, sometimes if the field is x is the field, let's say x is, last time I wrote it as a vector, f1, f2, f3, then some people write curl of x is equal to gradient cross x. Okay? And you should understand this language. I mean, because it means something. So let me just remind you what that means. I don't know if you recall the cross product. See, mathematicians have no idea what a cross product is anymore. They do something. You know what it is in terms of area, I hope. Yeah? Well, okay. So let's what I don't know when I was a child, I used to write I, J, and K here. Right? Those, yeah, did you? Write I, J, and K. And now you can write gradient, so ddx1, ddx2, ddx3, and now write the field here. Right? So as you see, I is the first unit vector, so the coefficient of I remember what we're talking about, we're gonna get, the curl of something's gonna be a vector, so we're gonna, the coefficient of I means what you get in the first thing here. So the coefficient of I is this determinant, by the way, the plus sign, this determinant is this operating on this, minus this operating on that, right? You remember last time what we got. This with a minus sign, okay, is this determinant, so it's this operating on this minus this operating on this. This with a plus sign, which is this determinant here, this operating on that operating on that. That's curl of the thing, or rotation of the thing. And you see why they call it then gradient across the field. Okay, so that's that language. Remember curl interval. Again, we have these isomorphisms here. We're going to fiddle around and do something here. I need to remind you how to get back to functions, because we're going to do something here and get a 3 form. And in order to interpret that as a function, we have to come back here. So the curl, the star operator, the Hodge star operator, from 3 forms, for example, of functions, or vice versa, is very simple. You take the given orientation form and just notice that a 3 form, omega, so let's call it, take a 3 form on n, say call it omega, and we know that it's a multiple of the orientation form that's given, and this gets mapped just to the function. Conversely, start with a function multiplied by the given orientation form. In this case, it's the standard orientation. So go back to 3 forms. That's the star operator there. The star operator here is complex. Remember, it was complicated last time. And we did it by defining star of dx1 which dx2. This is the basis. You have to fill this out, and I explain in the notes exactly what you're doing. You're filling this out to get the orientation form. The orientation form is dx1, dx2, dx3. So you fill it out and get it, so that's dx3. The next one, dx1, dx3. Well, you have to fill it out, so you put dx2 in there, and you have to put it in the middle, so you go across one. So it's minus dx2, and star of then whatever's left, dx2 which dx3. You have to go across 2 here to put in dx1, so you luck out and you get a plus. So those are the basis elements, and then every 2 form is a linear combination with functions as combination of these things, and star is then a module mapping that maps those 2 things back and forth. This is the case in dimension 3, where you have a given orientation form, and in your subject you do this all the time without thinking. It's just, you know it, and people in the applied sciences really know why these things are called curl and divergence. Because curl is some infinitesimal rotation of the form, and divergence is how the vector field. And divergence is you can see the field diverging or not. Yes? So it's really, so again, divergence is defined in exactly the same way, going from here to here and here. Okay. It's nothing more than translation. It's much easier than translating from English to Romanian. Okay. Now that was just the translation. Let's have some real fun. Let's have some fun. You want to solve a question, so some applied scientist says, I want a question given. Let's have some fun here. Where do you want to go? Let's start here, say a vector field here, and ask whether it's curl or something. So given y, does there exist an x with what would I say? Given y here I want to know if it comes from a curl with curl of x equal y. If you want to have some fun and write it in a horrible language, then this is the question whether this is the case. Given y, is it is there an x so that gradient cross x equals what? Solve the equation. What is the necessary condition? Anybody can read it off the top line. The top, here's the top line. Given a 2 form, does there exist a 1 form so that d of the 1 form equals the 2 form? We know this is a complex. D squared equals 0. So a necessary condition is that the given 2 form is annihilated by d. Right? So you just reinterpret the d interpretation and this question is given a 2 form alpha, does there exist a beta, which is a 1 form, so that d beta equals alpha? Right, that's the same question, because this is just the top line of this question. Okay. So we learned necessary condition at the level of the d interpretation is that d of alpha equals 0. So if you're starting something here, you're not going to get it in the image unless d of it is 0, and you maybe don't even get it then, as we know. So d alpha equals 0. So in the applied science interpretation, i.e., in the above interpretation, what was given here? Given y. So what we have to think where y is here. The interpretation was d is 0, so it has to be divergence free. One says that divergence free is the lingo here. This is jargon. I.e., divergence of y equals 0 is a necessary condition. Okay. So you want to solve the equation gradient cross x equals y. You need the condition divergence y equals 0. You want to solve the differential equation d beta equals alpha. You need the condition d alpha is equal to 0. It's the same thing. Okay. Now I did this for R3, where the answer to this question will always be positive, but in general, for some domain, for example, for in some manifold or even a domain, some open set in R3, it doesn't matter. It's a good enough example. There may be second de Rham cohomology, maybe not 0. So that means there are problems, i.e., the kernel of the D operator from 2 forms to 3 forms. That's what we're doing here. Modulo the image of D from 1 form to 2 forms. This could be non-trivial. And if that's non-trivial, then there will be differential equations you cannot solve. You understand what I'm saying? You will not solve, and the reason will be topological. This is a topological thing. If you know anything about topology, this is exactly the homology of the domain. Okay? So I will talk about that. I will just write down an example now, since you don't use the fancy word homology and so on. But just think the geometry may be non-trivial. It might have some holes and various things in the domain, and this will cause problems. So let's do an example. Let's change R3 just a tiny bit. Let's just remove the origin. Yeah? And you will believe me that, maybe I will assign this as an amusing exercise, it's very easy to solve, that this second de Rham cohomology of D is in fact equal isomorphic to R. And I can write down a differential form here which spans this. Okay? I will even in an exercise, maybe I will tell you what differential form alpha is not exact. You understand what I'm saying? I'm looking here, maybe to be precise, I'm trying to, this is equivalence class in the second round, is the second round cohomology. So I will write it down, and you will believe me when I say it's topological, because R3 minus a point, well, what the heck is R3 minus the point? R3 minus a point, here's R3, and then we take a point out. Well, I learned this from my sheet. You know, before the class, I write squares here, and then I go. I have to have fun doing this, you see, otherwise it's too boring. So you see this point, and in R3, and you see, for example, the unit sphere, and you see that in a smooth way, you can take R3 and bring it back to the unit sphere from outside and bring it up to the unit sphere from the inside, because I took the point out, right? This says in the lingo of topology that the unit sphere is a strong deformation retract of the full space. This is very strong. I can even tell you what the retract is, how to retract the whole space onto the sphere, holding the sphere confident. If you can do that, it maps the topology of the whole big thing onto the topology of the sphere, whatever that means. You can even write this as a homotopy operator on this de Rham complex. So the point is, you see somehow the unit sphere is a non-trivial class. And you can believe me that if you take the orientation form on the unit sphere and just pull it back to the whole thing, that's going to be the thing that's going to be non-trivial, because it's the geometry of the unit sphere that's causing this problem. So I will talk about this at some length. They're very amusing problems here. And topology in mathematical physics is of fundamental importance, and it's becoming more important, I think. Most people will agree.
I have a question, Professor. How
Yes.
do you define the theorem of D?
Huh?
And how do you define the theorem of D? Because previously we defined it on the whole manifold, but now...
The same thing. Let me just write it again, since maybe my notation is confusing. Let me just write it again, okay? So de Rham of anything. I mean, D is now n. I mean, I just changed letters on here, but okay, it's true for any manifold. So, in other words, closed two forms modulo exact two forms. Okay, that's what we're dealing with on D. Right? And the point is, as you will see, as soon as I pull that point out of there, I can find a form that has a big singularity there that reflects somehow this topological thing. Just like we've done for the circle in R2. As soon as I pull that point out of there, the form I wrote down, d theta, if you write it down in x and y coordinates, is y dx minus x dy divided by the norm squared. So it has a big singularity at 0, and you'll find the same form, the same thing in dimension 3. Okay? And that's what happens. So it's very possible that you cannot solve this differential equation. It's very possible that in this applied science notation, you cannot solve this curl x equals y. And the reason is usually some singularity that's living outside your manifold. We joke about having a pole in the hole. There's the hole, you have a pole in the hole. You know this from complex analysis, you get residue. It's something, you usually expect some sort of residue, and that's what's going on here. Okay. So that's what's going on. So sometimes you have 0 and sometimes it's not. And the theorem now that I want to talk about is Poincaré, so-called Poincaré lemma. I mentioned it at the outset. And the statement is that if M is diffeomorphic to Q, maybe I should say once and for all what a cube is for me. A cube, I will use what a cube is. But you see, if I said that M is diffeomorphic to a cube, M could be really a terrible thing. You know, there are lots of things diffeomorphic to a cube. So a cube is, what I mean by this is, say, x1, xn, I don't know. Let's put the origin in this. So that -1 less than or equal to xi less than or equal to plus 1, all I. Right? Square, so on, right? Cube. Obviously it doesn't. You see, if I allow, well, let's talk about this. For this theorem, note that the de Rham complex of M, so if phi goes from M to N as a diffeomorphism, then the whole de Rham theory of M gets mapped isomorphically over the whole de Rham theory of N. Right? Look at this. Look at the blackboard. Where the heck is the blackboard? Here. Yeah. You see, the one forms get mapped to the one forms. The two forms get mapped to the two forms. The three forms get mapped to the three forms. The functions get mapped to the function. And the key issue here is that phi star equals of D equals D equals of phi star. You pull back a differential form and take D, it's the same thing as D, and then pull back the differential form, and this is just some formal fact. And that means that this mapping here, it goes backwards actually. Think about it, this is phi star. So to get backwards, it goes this way, right? So since it commutes, that means that all of this discussion here commutes, absolutely everything commutes. And the de Rham cohomology is just an isomorphism and so on. So this statement here, this fancy statement, diffeomorphic to a cube, is just formal. It's because diffeomorphism doesn't do anything here. Okay? It doesn't do anything. You got it?
Can we finish this lemma? Is it finished?
Huh?
Is this lemma finished?
No, this lemma is the stupid part of this lemma has been discussed. The stupid part is I don't need to prove it for M, I just need to prove it for a cube. Right? I say everything's invariant under diffeomorphism, so let me just write here. This is good. Yeah. Very good. So this means you must only prove the contour lemma. For Q. Okay? Because if you have something diffeomorphic to the cube, it just goes by formality. Okay? Okay, let's prove it for the cube. Ready? Proof.
No, but
Hmm?
don't you have to still write the
We don't
the
have to
Poincare
say
lemma?
Oh. If,
That's why.
yeah. Well, since I didn't write it, I'm finished. I'm sorry, you see, I remember what I wrote at the beginning of the lecture, so here it is. Okay, but let me spell it out. Let me spell it out. Every closed Q form is exact. Let me spell it out in that way. Right. That's a statement that this cohomology is zero. That's a statement that kernel divided by image is zero. Okay? Every closed Q form is exact. And then you have the interpretation in the applied science notation. Right? If you have a form who's, for example, divergent, free of divergence, and the manifold itself is R3 or Q or something, then it says the form is kernel of another, a vector field is kernel of another vector field. Right? So that's important. So and the bad things happen at singularities where there's some physics going on. Yeah? You see, there's something going on there. Yeah, something going on at these singularities. Not just So we have no singular varieties for a cube. Okay, so here's a cube. So let's say given, say is a Q form alpha with B alpha equals 0. Okay. Now, and it's in a cube, so I mean I really have some variables here, and so I'm going to write these coordinates here as x1 and the remaining coordinates. That's a comma. x1 and the remaining coordinate. Okay. So in my picture, I'm always going to draw something like this. Here's the x1 axis, and here are the remaining variables. Okay? And somehow here is a cube. Here's a cube. I'm always reminded of I've told you this story. I had a student from did I tell you this story about this student from some African nation?
Oh, yeah.
I'm drawing these, yeah, I told you about these stories. Yeah, didn't tell you about this story. Yeah, in China you're very abstract, so you can handle it. But, no, it's really very interesting. We are used to drawing pictures here in Europe, I think, of some very complicated phenomena on the blackboard, right? Simply on the blackboard. Here's a curve. This curve is probably 20-dimensional or something. I don't know, right? So I draw a picture of this of a curve, which actually was going to be a torus, and I drew it like this. So I'll draw you my favorite torus. Maybe it looks like this. This is, if you don't mind, this is my favorite torus. And well, the torus. Anybody who knows algebraic geometry will know this is torus. Okay, you should think of this as a 2-to-1 cover of the plane. Well, downstairs is the Riemann sphere. You're taking complex analysis in one variable. So downstairs is the Riemann sphere, and upstairs is a 2-to-1 ramified cover at 4 points. Now, so already downstairs is the Riemann sphere. Now this guy is saying the Riemann sphere looks like this, and he said, Professor, very manly, very nice to me. That's the Riemann sphere. It doesn't look like that. No, seriously, right? I mean, no. And then upstairs, that's a torus. And I said, yes, it's a torus. Professor, a torus doesn't look like that. Yeah. So what I had to do, of course, is say, okay, I'm lucky in this case because downstairs is really the Riemann sphere, and upstairs is a torus, and it's something like a map like this, which interestingly enough has a ramification. It's 2-to-1 everywhere. You see, here is a projection. It goes up through here, hits 2 points, goes to 1 point here, and then unfortunately here you get another ramification. Then back in here you get one here, and you get 4 points. Well, that's the picture. You see, but that's not relevant for our discussion, right? It's not important. On the other hand, just because you can draw it as a torus doesn't mean you understand it either, right? So what you want to do is draw your pictures that are relevant for the discussion, right?
Always a line.
Huh?
I told you that you're always drawing a line for us.
Yes. Yeah, I always draw some trivial pictures, so this points out that
A line for everything.
everything is trivial, right? It is. I have only one picture. That means mathematics consists of one thing. Okay, this is a cube. This is a cube, right? And now, the naive idea is to isolate this variable, and we have a point here somehow x, and this point x is equal to x1 x prime, And the idea would be to integrate along this line the given form from 0 to x1 along this curve and hope that we're lucky that we have it right. You understand what I'm saying? You give me a form, and somehow or another I want to find, so alpha is given, so let me just write here with you. So we need to find I don't know, let's call it new form mu, so the d mu equals alpha. So the idea would be somehow or another to integrate this form alpha along this curve to get a form of 1 degree less. Again, this is a naive idea, and it doesn't work right off the top. But if you have the second idea, usually the first idea is wrong, or a little bit wrong, or absolutely wrong. But the second idea can be a perturbation of the first idea, which can be right. So in order to do mathematics, you must have the first idea, right? You can't just start someplace in the air. You must have the first idea and then move it. So the idea here is to take alpha and to isolate. Well, I said I wanted to integrate with respect to x1 somehow or another, and I'm going to optimistically say, well, alpha is equal to beta times this dx1, and then integrate, and I'm done. Right? Yeah, but that's nonsense, right? Because alpha, this form here has dx1 terms in it, right? Because automatically, something wedged dx1. There may be terms in alpha that don't have dx1 in it, so this is a stupid idea, but no, it's not a stupid idea, it's the first idea, and then you say, let's add on the remaining stuff, right? So you have the stuff that has dx1 in it, and that's going to be important for our integration from here to here, and then you have the stuff that does not have dx1. So that says dx1 is not involved by the way, in either one, in beta and gamma. And somehow, this is going to be useful, we think. Well, let's see. Let's try it. Let's try mu equals the integral t goes to 0 to x1 beta of t x prime dt. That's what I said. I'm going to integrate along that line, right? Now, please understand what the devil that means. Beta is a differential form, right, in x1. Well, dx1 is not involved in beta. So if you write it down in coordinates, you will have such and such with dx2 and so on, such and such and such and such and such, but you'll never have dx1, right? That's the point. I factored dx1 out. So you have all this other stuff, which is a form of 1 less degree, right? Doesn't have dx1 in it. And these coefficients, however, involve x1 because they're functions. They're functions of x1, x2, x3, x4. I can't just say the coefficients are, the coefficients involve x1, x2, x3, but I do not have dx1 in the form itself, right? Okay, so I integrate that. And let's just see what happens. So d mu, well, okay, let's see what happens. First of all, when I take d mu, you know what I do when I take d of a form. This is what we talked about as Leibniz, so there are coefficients, and then the dxi's. I don't want to get on your nerves writing the dxi's all the time. Okay, so here is this. So what we get here, this thing, what is this thing? This is d beta, well, d of this is d beta, I hope, wedge dx1, and let's see what happens. Well, that is going to be nonsense. That's only the first part if I differentiate it with respect to x1. Right? You know how to differentiate a form. Maybe I have to write this down. You understand what I have a form that, I have a form fi dxi, and I'm going to differentiate it, and I'm going to have the derivative with respect to x1 of fi dx1 dxi, and then the derivative x2 dx2 dxi, and so on, right? So what I did here, I have the derivative x1 of this, okay? And, okay, I hope I'm doing this right. Plus, so what am I doing here? No, no d. No d. No d. So, the integral from 0 to x1 of something, differentiated with respect to x1, is stupidly something. Right? Is what you get inside. Right? So, I differentiate first of all with respect to x1, and I have what I have inside, but I'm taking the differential form of it, so I get dx1 also. Right? The derivative of the coefficient, and then dx1. Right? But now the dx1 will come out in front. It will be the differential of this thing, and then dx1 will come out in front. So I need to make the sign right here. I need to make the sign right. It's -1. See, I have to push this dx1 all the way through it to get it right. So that's to the q minus 1. Okay. So then I'm in business. I get this, but I have some remaining stuff. I have to differentiate the rest of it. Here we go. This is going to be terrible. The d operator with respect to the second variable of this thing. Okay. Before we go any further, let's make sure we're all on the same track here. Okay? The d operator splits because we have coordinates into the d operator in the first variable plus the d operator in the remaining variables. Right? Right? This is completely clear. That's the big advantage of a cube. Right? So I took first the d with respect to the first thing, and what I got is I took the d with respect to the first thing, that's x1, that's where I got this term. Then I have the remaining d here, and of course, that's not involved in the integration, so I bring that inside.
And why can you put the differential operator inside it?
Huh? That's some stupid question. I don't. So, you want me to talk about the Lebesgue integral, or you want me to talk about Fatou's theorem, or dominated convergence theorem, or some fancy nonsense in measure theory? These are C infinity functions, Riemann integral. Yeah? You worry about if I have a C infinity function of bringing the thing inside, or what are you talking about? No, seriously, what are you talking about?
No, I don't know this one. That's why
Okay. So, what Mihai's, let's go through it. I mean, this is a place where we need to learn mathematics. Do you understand his question? They don't understand your question because it's so obvious to them in physics you can do this that they never ask that question.
exchange differentiation
You
for breakfast.
Yeah, so he's probably been in some course where they have the Cantor function and the characteristic function or the rational numbers or some idiotic thing, and you worry about that.
Yeah, but sometimes it goes wrong.
Yes, but if you have smooth functions, depending smoothly on the parameter, then it goes through. Shall we prove it? No, you need to prove this, Mihai, if you haven't done it. I'm serious. So that's one of the problems with beginning mathematics. You talk about every pathology in the world, and nobody has these pathologies. So, okay, let me give you a proof. Okay, you have integral from dings to, I don't care what it is, over something, yes, f of t and the variable you're integrating with, right? And you differentiate with respect to t. That's what you're asking about. Well, you write the derivative down. So it's the inside is f of t and x. So you write down f of t plus delta t x minus f of t x divided by delta t, and you make an estimate using the Taylor development of the C infinity function that it works. You see? Well, why are you depressed about this? No, it's a great question, but it reflects problems of mathematics education that in any case that you really have in the world, particularly in physics, right, where you have reasonable functions you're dealing with, this is a joke. And you should learn the jokes first, and then later on you have very non-trivial functions, right, where this is wrong. You can't do that, right? But you should learn what is a joke and what is non-trivial. You should not start with non-trivial. You should start with a joke, right? I think everybody agrees with that, right? You know a theorem. If Fn goes to F uniform, I hope you know this theorem. You know I like you, you're a good guy. So if Fn goes to F uniformly on compact sets or something like that, then the integral of Fn converges to the integral of F. You know that? It's the same theorem. Give me a break. It's the same bloody theorem, right? You just locally do this thing and it goes uniformly, right? Because the thing is C infinity. Yeah? That's the first application of the theorem. Okay. But I'm very happy you asked this question. 90% of your questions make me happy. And this makes a physicist happy because they knew you could bring it inside the integral anyway, right?
There's a theorem in physics that all functions are C infinity, except for the ones which I know.
And they're piecewise C infinity. No, it's a good question. Okay, so let's look what we got here. I brought it inside. Okay. And now I'm interested in this thing. So I haven't invested anything yet. So d alpha 0, right, equals 0. And where is alpha here? There it is. This is d beta, no, it's beta dx1. So this is d of beta dx1 plus gamma. Okay. Okay. So now, you see, now this thing does not involve x1, dx1, and this thing doesn't involve x1 either, right? So this is a statement that d beta x1 equals minus, I hope I do this right, d beta, this what is happening here? Yes, you see, when we take the x prime derivative of this thing and wedge with this, we have to get the x prime derivative of this. So this says the following fact, yeah, except for a sign. I'm not sure about the sign yet. Do you see what I mean? Is this correct? So we take the x prime derivative, the x prime derivative, the x prime derivative here, right? This doesn't involve x1, except the coefficients will involve x1. And the x prime derivative here, yes. I hope this is right. So Yes, this is correct. So you see what I'm saying? Do you also understand what I'm saying here? You don't understand.
I got lost.
Good, let's talk about it. Okay? You take the d with respect to these variables, right? You're going to get derivatives of coefficients, which of course don't involve x1, and then always dx1. Okay? Right? But you see, gamma, so whatever you get here is always going to have dx1. So to get 0 here, the only way you're going to get 0 here is to take the derivative of, what do I want? No wonder you didn't understand.
X1.
Well, I'm integrating with respect to that variable. So, x1, I'm sorry. You see? You see that yet? Anna, do you see that? So, again, we're interested in the differential of this thing with respect to the other variables. That's going to be equal to whatever this is. When you have those derivatives here, you will always, unfortunately, have this dx1. That's even good, because that means to kill it with this gamma, you will only kill it when you differentiate gamma with respect to x1. And so the coefficient you're going to get is going to be exactly this. Okay? Okay, well, we're finished.
Professor, can you write out more explicitly how could it be 0 if you plug in dx prime beta and 0?
Okay, first of all, d alpha is 0. I mean, that's the assumption. Second of all, that means this is 0. Third of all, that means I put this on one side and I put this on the other side with a minus sign. Okay? Now, what do I do when I differentiate this thing beta dx1? Well, I have two variables in this differential operator, x prime and x1. But I've already got dx1 here. So when I hit it with that variable, I get dx1, dx1, and that's 0. Right? So I'm only getting it when I have d of this x prime variable times dx1. So if you like, I could put d of the x prime variable, wedge dx1 here. That would be more clear, right? Let me do that. You see what I'm saying? Yeah? Okay, well, I won't do it, but I mean, that's what I would do. And that means that has to be equal to d of this with respect to the x1 variable also, right? Well, I just forgot the x1s, and that's what I have, okay? Now, there's probably a sign mistake here. Is there a sign mistake?
Looks right.
Yes, there's a sign mistake. -1 to k -1. Because, you see, what will happen is that if I take dx prime here, beta, I will get all the stuff and I will have dx1 on the end. And when I have here the dx1 term, I will have it on the beginning. So I have to push everything through to get them lined up. Okay, so you see I proved one very well, I think. So d mu, here it is, equals beta wedge d x1. I might even be lucky on the sign. Yeah. Okay. -1 to the k -2 d x1. And right, so -1 to the k 2k -2 times the integral d gamma dx1. Right? Okay. You see, I had the minus sign here, so I bring this to your front, I get k -2. But what I had here to collect the signs correctly, I had q -1 here in the first place. So I would have what do I put, I'm sorry, Q. I knew I was gonna make this. Ah, no wonder you were looking at me like I'm an idiot, because I am. I knew I was going to make a K, everything's a Q form. And these signs occur because everything's in the wrong order. I probably could have given a good lecture and they would have all been in the right order if I planned it. And of course, you see that's plus, and you integrate this derivative, and you get it. So, that's
Stupid question, how is 2q minus 2, q minus 1 plus q minus 2?
oh, you're right, Q is odd. So there's something wrong, you're right. Oh, I was being very happy about this sign. I hope this is Q minus 1. Let's see.
It's q.
Huh?
It should be q minus 2.
Q minus 2 is.
What?
Yeah, it should be minus 1 to the power of q.
Huh?
I mean, in the end, it should be minus 1 to the power of q.
No, you have this thing here. I have it. Shall we try to find this, or let's try to find it.
It was right.
So this is the definition of mu. So the sign, and I'm sure the sign is correct. I needed to move this through 1. And then the sign here is correct to make this part correct. And what I forgot to write here, okay, very good. I forgot to write minus the minus 1 that I put there, minus 1 to q minus 1. Okay. Now, this thing, where did I get that minus sign? Oh, this minus sign has to be there because I had to bring gamma on the other side. Okay. Now, why did I say this is q minus 1? Maybe this is q. Why is it q minus 1? Why did I say q minus 1? D. Why did I say q minus 1?
Should be Q.
Because when we differentiate that, we get dx1, and I have to put it through q minus 1 terms to get it over here. Somehow I'm off by 1 sign.
But gamma is the Q form.
Oh, gamma is a q form. So I have to push it through q terms. Okay. You see? Okay. I'm sorry. So
gamma.
this is correct, and this is.
Why suddenly gamma becomes a q form?
Huh?
I mean,
It's a q form.
Alpha is a Q.
oh,
Yeah, it's a q form.
okay.
So we have to push it through q terms to get it right. Yeah. Okay.
Professor, the thing is that the minus 1 times minus 1 to the power of q is equal to minus 1 to the power of q plus 1.
Well, but it's the same.
Oh, yeah.
Q plus 1 and q minus. Very precise. Ah, yeah. No, but no. It's very good because you see, in this thing, this becomes just 2 q's. That's what you were saying before, right?
Yeah.
Bravo. So we don't worry about even numbers. I'm terribly sharp, but it's a good exercise. Isn't it beautiful? You just do the obvious integration using the fact that you have a q and simply write down the answer, and that's Poincaré's law. Okay. Okay. That's very nice, right? It's Poincaré's law. Well, thanks for your patience, and now let's start our introduction to integration. This will be very brief. decided something I'm going to do here at Jacobs. I'm going to give this course where I try to give more and more over the years indications of the physics that I can understand. And every other year I'm going to give a course, so people can take 2 courses. Every other year I will give a course where it's much more mathematics intensive, so I will prove some of the things that I have not proved here. One of the things I will prove in that mathematics intensive course is the rank theorem, because I noticed it was never proved. Another thing I will prove is Stokes' theorem. And such theorems that are, say, maybe the proof of which is more interesting for mathematicians, I will give in that course. Okay, but here I will only sketch the integration theory. But I hope I can convince you it's okay. So the first thing is we start with this oriented manifold. The first thing to learn is I know there are attempts to integrate on non-oriented manifolds, and I've seen them even due to Durham and other people, but I just reduce it to the oriented case always. So let's have an oriented manifold. So this means that omega is a non-vanishing n-form. Now, I'm going to talk about something here, about the definition of an integral. Okay? I think this is a non-trivial subject, so it's maybe worthwhile thinking slowly about it. An integral, of course, is a functional, right? It maps forms to numbers, right? It should be linear, right? You add, yeah. Okay. So it's some sort of functional on top forms. Right? So the first thing is just, I'm sorry, I mean, I know you like to think of an integral as area under a curve and all that stuff, but one should think a little abstractly. N is the dimension. And now behind, you rightfully will ask, I'll give you a break, give me the question. I gave you the provocation. What's the question? It's a good question. Well, can I integrate every form? Can you integrate everything you know about and get a number?
Probably yes, since you consider the standard n form.
What?
Probably yes, since you consider the n form, the standard n form, and everything is f times that. Or
Well, I'm not thinking about subtle measure theoretic things, but I'm thinking about the integral from minus infinity to infinity of the number 1, pt. Okay? You cannot expect to integrate everything, right? So it's a functional defined on forms that you can integrate. Now that's really a circular statement, right? Now, okay, but of course, as you know, you should think of forms like this as being very good, right? And maybe what you want to define is a space of forms which die at infinity in a sufficient manner. Yeah, yeah.
can I ask a stupid question? Why do you draw a form like that?
Because a form, I use a Hodge star operator, and a form is a function. Hodge star.
Okay, so draw the corresponding function.
Yeah. And yeah. Yeah. So this whole theory is going to be, yeah, okay? And that's I really like that question because you see, this is a very, very nice question by me. So here's orientation 1 and here's orientation 2, right? And you might have the same form. That you're going to integrate, And, yeah, and then Mihai says, what did you just do? And I said, well, I just drew this thing by heart, right? But if you do the same thing here, it might be like that, right? So this is sort of you pointed out a very dangerous thing here, right? So a better thing is to integrate forms with compact support, right? Compact support has nothing to do with shape, right? Do you understand what I mean by compact support? So outside of some bounded compact set, it's zero. And that has nothing to do with anything, right? That's just a thing. So I would propose that we would define an integral on functions of maybe, let me just write the word compact here. Functions of compact support. Okay? Now we don't have to talk about, that's what I meant about conversions of the integral. You don't want to integrate from 0 to 1 over x, or something like this. You just don't want to do that. Right? Okay. Now, I think you should think about what is an integral. An integral is something that behaves well under change of coordinates. And this is really, you see, if you do supersymmetry and use, there's things called Berezinian integrals and all sorts of integrals that, there are integrals everywhere. And these things are always something that change correctly, the change with respect to coordinates correctly. Now, let's think about something you did learn in the first semester. Okay? It's called the substitution rule. I mean, you know what I mean. If you have an integral from 0 to 1, let's say, and you have a mapping, say phi, say the interval is 0 to 1, and you have a diffeomorphism which is orientation preserving from 0 to 1 to 0 to 1. So that's some change of variables. So substitution rule, change of variables on 0, 1. The integral, you know this, I'm not going to bother you. Integral f of t dt, let me just write it in funny language, is the integral of f of phi of t. What comes next? Come on, you can have a success here. Phi prime of t dt. Right? Now, I think it would be very good exercise for all of us during the weekend to think about that property defines the integral. An integral is a function that changes, that behaves this way under change of coordinates. Functional, which I guarantee you, that can be the definition, and I think that is the best definition. By the way, that's the only way you can prove anything, right? I mean, you want to calculate some integral, you find some good change of coordinates so you can do it, right? Right? I guarantee you, an integral, if you define it like this, an integral, additive function, you know some properties, that's it. What is phi prime? Phi prime is a 1 by 1, is a determinant of a 1 by 1 matrix, right? In higher dimensions, this says the change of variables by a diffeomorphism, if it's orientation preserving, which means the Jacobian determinant is positive, transforms integral is equal of f is equal to integral of f composed with phi times the Jacobian determinant, right? That is called the transformation rule of the integral. An integral, in my mind, is a linear functional which transforms correctly with the transformation rule. Yeah.
So you're defining again integration because you define.
I haven't defined anything. I'm saying what it should be.
Yeah, no, but you talked about integration of forms.
Yeah.
Which confused me really much. I mean, a lot. You confused me a lot when you talked about integration of forms, and you defined it with the pullback. But isn't it the same thing? The pullback and this thing?
Sure. What is the pullback of dt?
Decomposition.
It's prime of t dt. It's just the pullback, isn't it? So you see, this is the pullback. If this is the form, I don't care, alpha. This is the form E star alpha. Right? It is a statement that the integral is invariant under pullback by diffeomorphism.
You also have limits.
Hmm?
You also have limits. At least in your
Limit.
That's 0 to 1.
Oh. Well, in this case, I had something with 0 to 1 to 0 to 1. I'm sorry, but it could be from one manifold to another. Right, I'm sorry, thank you. Yeah. That's all that an integral is. Okay?
And Professor, one small thing. I think in the first integral, the t maybe is better to denote by w, for example.
I don't know.
What?
I don't know what. Yes, that's good enough. Anyway, that's some symbolism I don't even care about. But, right? You don't like that?
I mean, is it correct that the number on the second integral?
Let's go d. Let's just do Leibniz junk. D on the right hand side is p prime dt equals dx.
Yeah, I know this.
Huh? What's the problem?
No problem.
No problem. It's only the substitution rate. The higher, okay? Now, we need to stop, but how would you define an integral over a cube? I think you've talked about this in math, in engineering and math science, 1A, over a square. How do you define it? You're nodding your head.
You define it by Fubini.
Huh?
You define it with two double integrals.
It's usually written as a double integral, right? And that's, of course, the way you define it. You define it as you make these little strip pictures that everybody's made since it, yes? But you're defining it by the truth of Fubini theorem. Fubini theorem tells you how to integrate a double integral, but I mean, you're defining it by Fubini theorem, right? So for a cube, you know how to do it. Okay? Good. Now, if I have a non-trivial manifold, like a domain with a bunch of holes in this thing, and I say, here's a cube. Yeah, this is like my student from Cameroon, it's Professor Huckleberry, that does not look like a cube. Well, here's a real cube, an honest-to-God cube, and you take an orientation-preserving diffeomorphism from the honest-to-God cube to the abstract cube, and if it transforms correctly, you know that the integral on the image cube has to pull back the image over the cube here in Rn. In the cube in Rn, you've defined the integral in math EMS 187. Right? Right? So you know how to do it. Okay? You know how to do it. Right? And then some guy says, and the guy from Africa is really worried about this because he's worried about all this junk in here, and I don't blame him, because everybody worried about this until 1948, when Dieudonné explicitly defined partition of unity. And he said, you can have these things with compact support, with support only in the cubes, and they sum up to 1. You take some horrible thing, and you sum it up and break it into these parts, and you really only have to integrate over a cube. You pull it back to where the Cameroon guy's incredibly happy. You integrate over this cube, you add it up, and you go back up, and that's the definition. Right? Now, that is completely correct. There's only one thing to prove, that is well defined. You see, this depends on the cover, on the partition of unity, on everything you see that I just said. And to prove that it's well defined, there's only one theorem, and that's the transformation rule of integrals. The transformation rule of integrals on the cube, on the Cameroon guy's cube. Okay? So as soon as you prove that, you prove that the integral is well defined, you have to work in general, and I will show you how to prove Stokes' theorem in one line after you prove that the integral is well defined. The only problem is proving the integral is well defined, and implicitly you're proving, I don't know where I've written it or not, the integral of over m, so you have a map from m to n, the integral of the pullback of a form over m is the integral. This is the only thing that defines an integral. And if you have even in odd coordinates, in a Grassmann algebra where if you have some supersymmetric situation, for example, where integration is really tough because you have odd and even variables that don't commute, it scares the daylights out of you. It's a terrible thing. This is what an integral really is. It's something that transforms correctly. Okay, thank you very much.